ABC 1245.
Okay. Right, guys. Good morning once again, and let me introduce myself. I'm Captain Asad Galani in the School of Faculty of Nautical here, and can I have a quick round of introduction yourselves, please? So.
Hi, my name is Volkan, and I'm a naval aspect engineer. And I graduated from Istanbul Technical University, and I'm doing my PhD now on human factors and in the maritime safety culture. And also I'm working in a EU project which we are trying to transfer technology from aviation to maritime.
Interesting. Has any of your friends been studying here with us in the past?
Probably I don't know, but
in the nautical.
And what we have done is like we asked in the within the project.
Right.
We asked in the beginning of the questionnaire.
Right.
I don't know them, but we also asked help from here, and like many people is still questioning. But my supervisor contact with here probably better than me, but I don't know.
All right.
Anybody go ahead.
Okay.
Hi, good morning. My name is Saleh. I'm from Saudi Arabia. I have a qualification as a conductor. I served on board several types of vessels for 1 year as a cadet.
All right.
Then I worked on the Zid Transport as a yard and vessel planner.
Right.
Container terminal.
Okay.
Now I'm here. Take my degree.
Very good.
Good morning, my name is Mohammed. I'm a PhD student here in South University. I'm doing, actually my research is about enhancing navigational safety through field situational awareness and teamwork in the bridge. I had a qualification of second officer from Singapore, job on board tanker and container or road container vessel, also passenger. I worked as a VTS operator and Jet Islamic Port.
Jet Islamic Port, all right. Okay, that's good.
Hi, my name is Hisham from Saudi Arabia. Science background with license sport. Worked as a supervisor in the jet transport and
right.
Supervisor, and now I'm doing a PhD
on what?
Automatic collision avoidance.
All right. Okay, that's interesting. So, guys, I welcome you all at City Plaza College, Faculty of Nautical. So basically, like three of you have had some sailing experience with the facility, right? Not yourself, that's fine. So, guys, today I'm going to be talking about stability in general and some elements specific to the gas carrier. Okay. So let me give you some background. You may have had certain lectures earlier on. You may have been already aware of the cargo that it carries, the shape of the vessel itself. So I'm starting with the stability and cargo loading limitations. We'll be talking about more about stability, but this is just to form some basis as to what we're going to be talking about. If you have any questions in between, don't hesitate to just ask me. If things are not making sense to you, just ask me to stop and explain again. Okay? So just feel free to just flag up your queries anytime you like. So we were on stability and cargo loading limitations on such ships like gas carriers. In particular, stability and stress calculation. They must be performed for the cargo expected to be loaded and discharged, and immediately the cargo watch intermediately the cargo watch officers should perform the stability and stress calculation at least once every watch. Now, fine, we're going to be talking more about stability later on, but the other element that you see is stress, right? What do you understand from that? What do you think? I mean, you don't have to be very technical here. Think of a ship, and if I'm talking about stresses on the ship, could you tell me what am I referring to here? what sort of stresses do you expect a ship could have? Maybe at sea?
Side and hugging.
Hugging and sagging, well done.
Bending,
Very good, absolutely. Yeah. So,
Water pressure in very high, very deep draft places.
okay, water pressure acting on the shell or the hull plating. Yeah. So, I'll be elaborating on the hogging sagging business here. Okay, referred to as longitudinal stresses, and also the one that you referred to about something about twisting. And this twisting business is called torsion. Okay, right. So, as I said, we will be talking about that in detail in a minute or so. And now coming to stability. So, regarding stability, what is it that you would expect the vessel to be, undergoing at sea or in harbor with regards to stability? So, and what exactly do we mean by stability of a ship? Any guesses will do. Any rough idea?
Keep floating in the outside.
That is the whole idea.
The distributing for the cargo.
Yeah. So, would you agree? Like,
Yeah, it's
Yeah.
like basically we define stability as a kind of the reverse effect which will keep the ship
afloat.
afloat.
So, when you're saying that, would you agree with me that when you say stability and you said this is the reverse effect of the weight of the ship acting or weight of the ship exerted in the water? So can I say weight of the ship in the water is equal to the buoyancy, and that's why when the two balance out, it keeps the ship afloat? Right. So again, we're going to see more of it. So since the time is a bit limited, let's move on. Oh, sorry, using the wrong computer. I hope I haven't switched off anything there. Right. LNG carriers have tanks with large width, be it a membrane type or a MoS type. The tank width or the surface area could be large. Therefore, they will be subject to reduction of intact stability due to free surface effect. Now, free surface effect, I've actually printed that in bold, is something that happens when the liquid surface within the tanks is free to move about, right? So think of a ship that is rolling in the sea because of the rough seas, yeah? And the liquid contained therein will also move with it. And that may cause some implications, some complications in terms of, stability. So, like any other vessel, the LNG carrier must meet IMO intact stability requirement or criteria when fully loaded. So, in short, any ship, including LNG or gas carriers, must comply with the minimum intact stability criteria. That's something that we're going to be going over with you. A vessel may become unstable when multiple tanks are slack. So we talk about multiple tanks which are slack, free surface being created, and free surface if it goes out of limit, it may have detrimental effect on the stability of the ship. Again, this is just to form basis. As I said, we're going to be seeing as to what exactly free surface effect is all about in a minute. So, unstable multiple tanks are slack during cargo or ballast transfer operation while bunkering or in intermediate states or stages of loading. Even though the trim and stability manuals generally deal with arrival and departure condition, a person in charge must work out the stability requirements or stability calculation for the entire passage, right? So it's not only about the arrival condition or the departure condition. What's happening during the voyage should be taken into account as well. Oh, but then why do you think that things might change during the voyage? Is there something happening during the voyage? Let's say you have a week-long voyage at sea.
Water density.
Okay, water density.
Temperature, fuel consumption.
Fuel consumption. I like that. fuel consumption.
Water consumption.
So what if fuel has been consumed? Normally, let me just give you an idea. The tanks at the bottom basically carry either ballast and some fuel as well. So in general, the tanks are actually at low level, most of them. So when, sorry, your name was Abdul? Saleh. When Saleh said fuel consumption happening, I said, so what? If fuel is being consumed, how do you think it would affect your ship stability?
It will decrease the stability because like we always prefer to like put all the weight on the bottom.
I like that. I like that phrase.
Lower the GM, I would think.
Thank you so much. Absolutely. It's about making it bottom heavy. So if the ship is not bottom heavy and you make it like, or it tends to become top heavy, it will tumble over. Yeah? So you don't have to think hard on that, right? So it's better that the ship is kept bottom heavy. Right, so if you're losing fuel from down below, what's happening? Center of gravity of the ship keeps traveling up. And a time or a point comes when it may become top heavy then. Okay? Right, okay, so all stages of the cargo operations. A typical MoS type carrier there. Again, this is not part of stability, but just to make sure that you guys are comfortable with the profile or the cross-sectional view. And as we see, it's a double hull down below. We may have double bottom tanks, yeah? Engine room, pump room, and the LNG tanks, and see the level of liquid in there or the gas in there. It is free to move about. So apart from free surface effects, that we're going to see how it affects your stability. Apart from that, is there any other element that you may think could be a bit sort of not very viable for the ship with regards to the free surface?
The outside, maybe like.
Okay, let me put it this way. If I lower the level a bit more, let's say for this tank, if I lower the level,
the 6 will increase.
What will increase?
The 6 is free surface. 6 will increase, come more.
Yeah, okay, fine. Apart from free surface, apart from that factor, is there any other factor that may be undesirable at all?
Liquids create their own also frequency in ships, and if they like in the same frequency of ship, like basically moving, I don't know if it's in that area.
You mean the surface of the water? Can I refer to this as sloshing effect? Okay, the surface, and when the ship rolls, the huge volume or huge area we're talking about, causing the water to slosh over to one side, and think of the impact that it would have with the side plating. Okay, if the surface area is big, obviously the sloshing effect will be more, and it could cause damage to the shell plating. Yeah, or the membrane of the tank. Okay? So free surface and sloshing both may be a bit detrimental to the ship stability. Let's just quickly move on then. The purpose of showing this diagram is just to make sure that you guys have the right concept of the construction of the ship. Cross-sectional view you see for different ships here. We were referring to MoS type here. See the double bottom tanks? Do you think the double bottom tanks here, they're starting from here, right? And some of the tanks are going all the way up to make the ship double hull. See here, there's a watertight subdivision. You're looking at the cross-sectional view. If I put water in here, water may not be able to go to the adjacent compartment on its own, unless I open the valves or I fill the other compartment. Some ships may not have this partitions or watertight subdivisions, so they are all through and through, right? And such cases you may have a U-shaped tanks, okay, running all the way from one side to the other. They may have provisions works to close them, but they may be left open as well. Okay, so I will come back to this point and ask you a question on that later on. This was just to give you some idea. For example here, right? Although you can see a subdivision there, okay, but it may be served by a valve that could be open and closed. So if you leave it open, it's as good or as bad as having no watertight subdivision. So in this case, I'll let you think as to what could be the implications.
Will create also free surface effect. The
Yeah.
water will move. Also on the tank.
So, fine. I mean, do you think the free surface effect in this case based off, will be more or less than the conventional sort of a double bottom tanks or conventional side tanks? Would it be more or less in here? Okay, I don't want the answer right now. Maybe later on. Okay, you can keep thinking about that. Some of the points we can discuss quickly. It must be ascertained if the vessel meets the IMO requirement in taxability criteria. For all stages, as we just said, and we have discussed about these tanks, different types of tanks, which will produce free surface effect. Ship loading instrument must be used to quickly determine or verify compliance of the ship for the intact stability as well as the stresses. So, are you aware of that, or have you seen one? It's just a computer with the software that is ship specific, and all you got to do is just input some information, and the computer will do the rest of the work for you and the output. So, what sort of an input would you make?
Cargo quantity.
Cargo quantity.
Yeah.
Okay. And
Cargo plan.
cargo
Plan.
plan.
Yeah.
I would say no. I'll tell you why.
And also light ship, the weight of the ship, like the structure is important for the calculation of stability.
Maybe I haven't made my question very clear to you. I said that cargo loading or cargo computer has software that is ship specific.
Okay.
You get the picture now? That is only for that ship. Okay? So that means it is already knowing all the features of your ship. Okay? I mean the permanent features of your ship. So if that is already knowing, you need not tell the computer about that. So you would tell the computer about how much cargo you're loading. That's well done.
And how much ballast?
How much ballast? Well done.
How much fuel?
How much fuel? Anything you can come up with? Any other weight that you're carrying, you have to tell the computer. Apart from the weight that you're carrying, what else would you tell the computer? Okay, I'm carrying, let's say, 1,000 tons of liquid in one of the tanks. Very good, absolutely. I need to tell the computer the distance from different reference points. Reference point, I mean distance from the base, which is keel, vertically upward, as to how high the sphere is sitting. Then I have to tell the computer the distance from here, as to how far from the arc perpendicular I'm carrying. And then, if we have tanks on either side, then I have to tell how far away from the center line. Or,
But this kind of information considered as a ship specification.
yes. So now, if you are putting the weight in a particular tank, right, the ship should be able to work that out for you, because that particular tank is located in a certain position that the computer knows, right? However, distance from the arc perpendicular forward, computer should know. But the height, would the computer know already? If you just put in the weight, you say it's 1,000 tons put in this, would it be able to calculate the height of the liquid? And why do you need to know the height of the liquid? Why do you think the computer should know about the height? How much you can? You're telling the computer. Why? You have told the computer about the weight already. Why do you think you should bother telling the computer about the height? Well, height will have nothing to do. That is your ship, right? So, let's say one of the tanks, you have loaded it, 1,000 tons. Okay, fine. You told the computer that I'm loading in number 2 tank. The computer would know where number 2 tank is. So it will calculate on its own how far off from that weight is being loaded. My question is, why would you tell the computer about the height?
Because it's the height, it will understand like it's when ship is rolling, and it's knows the center of gravity.
Thank you, that is the key word. I like that. Center of gravity. So for all weights, the center of gravity must be known by the computer. In this case, the center of gravity of the liquid would be right in the middle of the weight. You agree? So that distance, the computer should know. If I increase the height, the center of gravity will obviously go up. So that is called, if that is my keel, the base, and this is the center of gravity, that distance will be called kg. So when we start stability, when I refer to kg, that simply means position of center of gravity of the weight above the keel. Then the ship as a whole will have its own center of gravity, right? And that I will refer to as a capital G. So maybe the ship's center of gravity as a whole is sitting here. So that will be given by capital G, and the small g is for the weights on the ship. Likewise, that distance will be called kg, capital K, capital G. We're going to be talking about kgs and gms in a while. Just to summarize this for you guys, loading instrument is there on all ships. Okay, every officer or person in charge must know about the operation so that before departure they can check whether the ship complies with the criteria. Now, if a ship does not comply with the criteria, it cannot sail out. It will be a crime to sailing out. So.
If I tell Sally, don't answer because it's easier for me. No problem.
Have you heard about the load lines, guys? Yes. Okay. Are you familiar with this diagram?
Yes.
Where do you find such diagrams on a ship?
Side of the ship.
On the side of the ship.
The middle.
In the middle. Yeah.
Yes.
On both sides. Now there are certain features on this diagram. For instance, you have an S, you have a T, the W, and so on. What do they signify? What do they represent?
Water density.
Okay, so right. So these lines are to indicate at different levels of drafts required area that your ship is in. S is for summer, T for tropical, W for winter, freshwater, and tropical fresh. Now, simply speaking, guys, one quick example. If I put the ship, okay, in a freshwater pond, automatically, which draft do you think ship should do? Now, if she was initially floating at that draft, so let's say ship was in salt water, floating at that draft, summer. And if I pick the ship and place her in fresh water, what will be her draft? What will happen, first of all, what do you think will happen to the ship as soon as I place her in fresh water?
Think more.
Think more.
The draft will increase.
And the draft will increase, and the draft should automatically go up to this level, F, fresh water. Again, that is typical to the ship. So automatically it should reach up to the top edge. All the draft marks are taken from the top edge of these marks, right? If the ship is in a tropical zone, then you can actually go up to this level safely. If the ship is in winter zone, up to that level only. So why in some zones you stay low in terms of a draft, whereas in some zones you're allowed to sink deeper when you sail out?
Density of the water.
Density, for all of them, the density is taken as saltwater density. We are assuming tropical, summer, winter, the density stays 1.025. Because these are only valid and applicable when the ship is out at sea. At sea, the density is 1.025. It's only the harbor that the density is less. So these are all for 1.025. So my question is, why different levels? Just think about it for a minute. Tell me. In some cases, they're saying, fine, you sink deeper. But in some cases, they're saying, so, stay low, low draft.
Usually.
Again, it's just about common sense. You don't have to be very technical on that.
Usually in fresh water there is no draft or ridge down at the bottom. So that's dangerous if you try that.
Right, okay. So freshwater, tropical fresh, something like that, right? So,
Okay, about the temperature.
temperature? No. Okay, let's say you are in summer zone and you have loaded your ship up to summer mark. If you're in salt water, you cannot go any deeper than that. If you do, you'll be actually committing a crime. You're violating the rule. You cannot sail out. Not even a millimeter above that you can go. If you ship,
maximum draft.
that's the maximum draft. If the density is salt water, right? So once again, if you're allowed to go up to this level, that means the ship was in tropical. Then that means you can load more cargo. Okay, load more cargo, sink her deeper, and then sail out here. If you were here, then you'll be loading less cargo.
Because like maybe, and for example in winter it's obvious that the weather condition will be, the waves will be much more rough, and you make a precaution to avoid it. Like in, for example in freshwater, you have seen that the waves won't be that bad, so you can load more.
How about tropical?
It seems that it's better than the summer.
Is that your own thinking? Is that what is it something that you dug out from your prior knowledge, or?
No, I'm just like thinking now. I don't have an idea.
Well, I appreciate it. Well done, I must say. Absolutely. See, I said this is all about common sense. So, think why in certain places you are allowed to just sink in deeper, whereas in some places it's shallower draft, lesser draft. So, absolutely right. Winter, they ask you to have, now, see this portion which is dry, which is above the water? You know what is that called? Freeboard. So, if you're in winter, they want a bigger freeboard. Just because the reason that you just mentioned, the seas are normally rough and they don't want the ship to be actually taking in water. Or, in other words, the seas or the swells breaking on your ship, okay, and flooding your ship. So they say, fine, if you're in winter, you take some measures meaning some precaution, and you go with a deeper freeboard. Whereas in tropical, you say fine, things are not as bad, less chances of ship taking in water, you taken a smaller boat. Problem. Taking more cargo, sinking more.
What if the vessel is sailing from winter area to tropical area?
If she is sailing from winter to tropical, as simple. Okay, that is the what do you call port in winter, right? And this is sea. At some point, the zone changes, right? Let's say that is a current point. On this side you have tropical, on this side you have winter. You must sail out up to the draft up to winter level. You cannot exceed because ship is in winter. When you touch here, when you enter here, you can go deeper. Take ballast if you like, or don't, because you're still complying with the zone rule.
Okay.
Because your draft is still less than that. Had this been the other way around, okay? Now, had this been the other way around, if you are in tropical, you load up to tropical, you sail out, and after 2 days, you enter summer zone. You have to make sure, you have to do calculation in advance that when I cross that line, my ship's draft drops down to summer. That means during this passage, maybe you're consuming fuel oil enough or deballast. You're lightening your ship here. You got to lighten your ship. Otherwise, again, if you enter with a draft deeper than that, you will be penalized. Okay, and that is violating the rules. It is not allowed under no circumstances. So again, it is the duty of the person in charge to pre-calculate everything, making sure that your ship does not violate the load line rules. Again, guys, something very childish, something very easy, but at the same time very important. If you need to get some idea about ship stability, you must know how your center of gravity and center of buoyancy acts at sea or in water. Think of this ship, and are you okay looking at this view? Do you know what part of the ship I'm showing you? Is this side view or is it the cross section? Cross section. I'm simply showing you the center of gravity of this ship when she's floating in water. The center of gravity acts vertically down, needless to say, right? My question to you is, if I push the ship, meaning by wind or by swells, if the ship heels to one side, that means rolls to one side, what will happen? What will happen to the center of gravity?
Change more.
Yeah. So this
If the gravity will stay, remain the same unless the cargo is moved.
Oh, really? So that's my ship. Wind blowing from here, causing the ship to heel at sea. You mean to say the center of gravity would move to the right? No.
Well,
will not move it.
He's right.
Stay the same unless the cargo is moved.
Absolutely.
The weight is moved.
This is something we must bear in mind, guys. Now, if the ship is heeled, right, the center of gravity would not move. Unless the cargo or weight is moved about. Because G is regardless of ship being in water or in dry dock or wherever, the center of gravity would still be there of the ship. It has nothing to do with water. So if you add something to the ship, meaning adding weight, it will move. Discharge weight, it will move. Shift weight, it will move. Otherwise, it won't move. Okay? So same applies to anything in the room. If I ask you where's the center of gravity of the table, you say here. If I put that computer here, it will move towards the computer. Simple as that. If I now take the computer off the table, center of gravity will walk away and come back to its initial position. Same applies here. So that's one thing. The center of gravity would not move when the ship heels. And the other thing is, as we just said, its position depends on the distribution of weight around the ship. Now tell me, what do you understand from me seeing those slides? Center of buoyancy. What is it? Center of buoyancy. The buoyancy force is the force exerted by the water, which is equal and opposite the weight of the ship. My center of buoyancy roughly, because that's the underwater part of the ship, my center of buoyancy would sit in the middle of the underwater volume. Now, let me just, once again, heel the ship by external force. When causing the ship to heel? What do you think happened to the center of buoyancy? Why? Give me the reason. Very good. I said the center of buoyancy would always sit in the middle, center of the underwater volume. If I heel the ship, let's see. Ship heeling, look at the underwater volume. All got changed. Therefore, B will move and seek the new underwater volume, new center of the underwater volume. So which way do you think it will move? Obviously towards the more volume. Will move here. And it will continue to act vertically upward. Because that's the property of center of buoyancy, to be acting up. So see the difference in the two? The center of gravity does not move when the ship heels, whereas buoyancy moves. Buoyancy moves, gravity doesn't. Let me show you both in one picture combined. And that is what stability will be all about.
Lifting lever when it comes to angle.
Yeah. So, you did your second mate's ticket, right? From where? Singapore. All three of you?
Yeah.
Right. How long back was that?
4 years ago.
Right. So, yourself, are you relating well with what I'm saying? Because I have a mindset that I'm doing things from the scratch. So I'm not counting on your prior knowledge actually. Okay?
I know this stuff. Like I have been taught in my second year of university of stability calculations, etc.
Oh, right.
Because I'm designing the ship, I need to know.
Of course.
And for example, in tropical waters, and what will be your the maximum degree of your and because I need to provide a ship to ship owner.
Absolutely.
If he says that I will sail in here and I want a stable ship, I need to calculate accordingly.
Yeah. No, I understand. So this is like designing and something to do with construction of the ship. So I think same applies to you in a way or the other. Yeah. Right. So if you think what I'm going through with you or going over the slides with you, if you have already knowledge of that, then I can skip that and go to a higher level slightly, something that I want you to, about stability. So
For me, I think we go graduate.
go gradually, okay.
This is my opinion.
Okay, so what I'm doing, I'm going a bit faster, knowing that you guys already know about it, just helping you recall,
Yeah.
right? And then when the time comes, I'll slow down. Okay? You are aware of K, you know about G. There's an M appearing now, which is called meta center. Okay? Now this, to just keep it simple, just take that as the point, a pivot point, okay, at which when the ship rolls, you come back. Now that pivot point stays in one position when the ship rolls to one side or the other. M won't change. But that statement is only valid up to small angles of heel, 10 degrees. Ship heeling up to 10 degrees from vertical, on this side or this side, M would stay in the constant position. So if I ask you to draw me an arc, you will have the center of the circle at M. Okay, that's about which the ship heels, up to 10 degrees only. So for the time being, that is valid. I want to show you first what's happening here. That is a ship that is heeled by external force, wind. I told you the center of gravity does not move. Center of buoyancy moves out of the center line. Initially, G and B were on the center line. Now B moves out. You can see for yourself. B is acting up, pushing it up. G is pulling it down. Now, if I remove the wind or the external force, what do you reckon will happen to the ship?
Back to normal.
Back to
normal.
And I don't have to even elaborate on that. That is self-explanatory that ship will get back to upright because she's getting a push from this side up, right? But how we explain this? We, instead of this big lecture that I've given, you can simply put it in one single sort of phrase that it is the GZ lever that causes it. So if I told you, guys, the ship comes back to upright because of the GZ lever, that simply means that it will come back because of the two forces acting in opposite directions and the distance involved between the two. So what is the GZ lever? Guys, for me, GZ lever is your stability. This is the nucleus of your stability, GZ lever. This determines your stability. This dictates your stability. The GZ lever is simply the horizontal distance between the G and the line of force of buoyancy. Now, the length of the GZ lever, as I said, dictates as to how quickly the ship gets back to upright. If at that angle, same angle, if my GZ lever was bigger, same angle of heel, let's say the ship is heeled to 8 degrees, and one ship is having a GZ lever that big, the other ship is having a GZ lever that big for the same angle of heel. Which one will come back quickly?
Bigger one. The bigger.
Smaller one.
Bigger one.
Smaller one will come fast.
Bigger one, I think, will come faster because of bigger.
Small GZ lever, less force. Bigger GZ lever, greater force.
Think like a momentum. You will want.
This is like a spring. You stretch it more, there'll be more force when you release it. Okay, you stretch it little, there'll be little force exerted. Same here. If you got a bigger GZ lever at the same angle, it'll come back very quickly, spring back quickly. If it is a small GZ lever, it'll take its time coming back because there's less force involved. Okay, less energy involved. You can put it that way. So bigger GZ lever, more stability. Small GZ lever, less stability. Ship is still stable. Look here, different stages. An upright ship heeling slightly, heeling more and more and more and more. Look at the different sizes of the GZ lever changing. Same ship. When she was upright, there was no GZ lever because G and B were in the same line. They did not get separated. But as the ship healed, a GZ lever got produced, got even bigger when she's healed even more. But then what's happening? After a certain point, if she heals more, the GZ lever will get smaller and even smaller. And at this point, now tell me why the B moves out, further out, giving you bigger GZ lever, but then at some point started to come back.
The underwater volume.
Because of the underwater volume, once again, guys, all got to do with underwater volume then. And it is a typical for all ships, guys. As you keep on healing the ship, the GZ lever goes out, B goes out, and then at some point it starts to reduce in size and zero. If I leave my ship here and see, no GZ lever, nothing to bring her back to upright, she will stay like that, and small push from there, capsize. Simple. So one should not allow that stage to develop, right? So this shows, guys, the bigger the GZ lever, more energy or more force for the ship to get back to upright condition. If I ask you, and you guys are all aware of how to construct curves, if I ask you to construct me a GZ curve showing the GZ values, now that is my x-axis, this is my x-axis, that's my y-axis. I want you to consider GZ lever size in meters and angle of field in degrees on your x-axis. Absolutely. So this is 0, now 10 degrees, 20 degrees, and so on. So if I say, okay, 0 degrees, when the ship is upright, the GZ lever is 0. 10 degrees, you get slight GZ lever. Yeah. Maybe up to here. 20 degrees, you get more. 30, you get more, and so on. Yeah? But at some point, it starts to reduce in size. And, guys, after that angle, it becomes 0. Now, at that, it's becoming 0. After that, it becomes negative. And when you construct your GZ curve, it should look something like this, typical shape of a GZ curve. Okay, so every ship, when she departs, the master, the captain, will have to come up with that. These days they have computers, so check on the computer gives you a printout of that, and the master gets satisfied. Okay, now what is it that he has to get satisfied with? Just by looking at the shape of the curve, say, oh fine, I like the shape, so let's just sail out. He'll have to check 6 things and put a tick mark. It's like checking the boxes. He has to put tick marks for all 6. If one of them is not complying, you must not sail out. You cannot sail out unless and until that thing is addressed. What are those 6 things? Okay. Yeah, I will speak about them. But any questions on the GZ curve? Right. Moving on then. I spoke about M, guys. And again, just to refresh your memories, I said take that as a point. Metacenter. This is called M metacenter. I said when the ship is healed up to 10 degrees, that is the point about which the ship will actually heal. In other words, when you come to define it as to what M is, it is the point of intersection of the buoyancy force when the ship is upright and healed. Remember buoyancy force acting upwards all the time? When you heal the ship, B moves out, still acting up. So if I ask you to imagine your first line of force of buoyancy and your second line of force of buoyancy when the ship got healed, tell me where the two meet. The point of meeting is M, meta center, in other words. So, simply speaking, this is the point of intersection of the lines of force of buoyancy. When the ship is upright and heeled. Coming back to my stability bit. That's a typical layout, guys, for a cross-sectional view, that you have a K, G, and M shown always. Kg, we know, is representing center of gravity of the ship above the keel, the distance. The Gm is again something very important with regards to your stability. We said Gz is stability, then Gz is governed by Gm actually. So every time when you're doing stability or dealing with stability, practically or theoretically, you'll be referred to GM. What is the GM of the ship? What is the GM of the ship when she's at sea? What is the GM of the ship when she's arriving at a port? So why do you think the GM matters to us so much? That distance. Why do you think that GM business is also so important for us? Does it have anything to do with the size of GZ then? But what angle are you talking about?
From M to Z to G, the angle up.
Right. Okay. So, no, okay, I agree. But my question is, does GM have any powers on GZ? Is it controlling your GZ? When I say controlling your GZ, I mean the size of GZ. See, I want my ship, when she's heeled, she develops good size GZ levers. I don't want the ship to be just coming up with small GZ lever when she's heeled. That's not good stability. I want my ship to be coming up with appropriate size GZ lever. So my question is the GM controlling the size of the GZ? If your answer is yes, could you tell me how?
As the M goes up, the GZ will be
May I add something? Like
Yeah.
some of the captains, like we had like some of the shipowners, they don't like too big GZ. They said like you are building ships too tender, like even like goes up and it makes them feel comfortable.
I agree.
That's why we are also
Very
trying to optimize.
I was waiting for someone to come up with this. That's why I was a bit careful choosing my words. I said appropriate GZ. I said I don't want a small GZ, I said appropriate GZ. Okay? I used the word appropriate. I did not use the word high GZ or very large GZ. You're absolutely right. If the GZ is very long, very big, then the ship will come back quickly. And then again we have disadvantages of that. And that is not called tender, that is called stiff. Tender is the one with the very small GZ. So it's one of the two things. It's a stiff ship that comes back very quickly. Tender is again not desirable. So both tender and stiff are not desirable. Tender means ship is heeled. Oh, she'll stay there. And then, oh, fine, I have to get back to upright, and then she slowly. That's not good. What happens if she goes to large angles? She'll stay there. And then she'll realize, oh, I'm heeled. Let's get back slowly. That is not good either. Large GZ, you heel, what happens?
come back up.
Oh, very fast. Things will be blown on the deck. Crew might trip over and cause injury, So not advisable at all. So my question back to my GM. I said, do you think GM controls the size of the GZ lever?
Yeah.
Look at the picture and tell me how.
One on the right. As long as the end goes down, if the G goes down, the GZ will increase.
Great, I like that. That's my heel ship. You got G there, and we can see the GZ lever being produced. What if initially my G was sitting down? If my G was initially sitting lower than that position, let's say the G was here. Now when the ship heels, your GZ lever will be bigger for the same angle of field. My GZ lever will be that big now. So lower the G, bigger the
Yeah.
GM.
We cannot control them, and we just could move the
Since we cannot control the M, but we can control the G. So it shows that GM, bigger the GM, bigger the GZ lever because of that reason. If you put too much weight on top, the G will rise up, giving you a small GZ lever for the same angle of field. Yeah? So it is the GM that controls your stability basically. Small GM, small GZ lever, big GM, big GZ lever. So, sorry, I'll keep asking your name, guys. Sorry for the irritation that you may have on that. Your name again?
Volkan.
Volkan.
You can remember from Volcano. It's called
No, Volkan. I've had a student by that name earlier on.
Okay.
Yeah. Yeah. And he was a good student too. Yeah. So, fine. Any questions here, guys? I don't want you to stress out on seeing what's happening here. The purpose of showing this right angle triangle is only to work out as to what will be the size of my GZ lever if I know my GM. I can simply work out through this formula, says GZ is equal to GM times sine theta. It is found through the right angle triangle, simply. Okay. So remember, guys, I said the position of M is only valid up to 10 degrees. If the shift goes after that, the M may not stay on the center line. If the M is not staying on the center line, then this right angle triangle will never be constructed. Okay, there's no guarantee that M would still stay on the center. We have other means then to work out the value of GZ, other formulas then to work out the value of GZ. But up to 10 degrees, it is simple.
10 degrees of
heel, 10 degrees of heel. Right. Guys, let's break for coffee then, right? And we should continue after the coffee break. I think you've had enough, otherwise it gets saturated.